Oh, hey, I didn't see you there. Just kidding. I know this video is about review and going over some of the problems and ideas that we've had before, but actually I want to take the time out to also let you know why I think this unit is important in general. Of course, I have stated that these circuits are the underlying idea of every single electronic device throughout the world that is integral to our modern society. Of course, I've mentioned that, and I think that's pretty cool. That's actually pretty amazing. But if you didn't think that was cool enough, this actually kind of references us. What? Maybe you already understand where I'm going to end up with this idea. If we are biological machines or not, or something else, you know, how all that works, which is really interesting stuff. That's why I like science and what it leads to. But yeah, we are one really convoluted circuit, essentially. Everything that you feel, that you think is governed by electricity. Now, it is a little different because most of the electronics, they have a current based off of electrons. And we are mainly based off of action potential, based off positive ions like sodium or potassium. All in all, it's just charge moving from from one place to another, which is allowing us to think and again, have these physical sensations. Like if I put my hands on this table, it'll be like, oh, it's warm, but not too warm enough to where it's dangerous to my body, or ooh, it's kind of nice and soft. And so I can keep it there, or I can, have in my head just be like, oh, this is kind of an ugly table. But, that's all governed by that. And let me kind of go over the history of how we came to this knowledge. Of course, this is basic for everyone now, but this hasn't always been the case. Now, let me take you back to a time where there was not necessarily a distinction between science and philosophy or religion or many other things. Everything was convoluted. So let me take you to the end of the 1700s. We had learned a lot. Of course, Isaac Newton had already been around. We had learned some of the basics of physics and science in general, but they're still learning. There's no distinct difference between some of the different fields of study even. So let me tell you about Luigi Galvani. Luigi Galvani. Now, this was a professor that actually taught about frogs' anatomy, and so needless to say, he dissected a lot of frogs, and he played around with certain types of other new materials that were related to electricity, because electricity was something that was kind of starting out and brand new, and it was the hot thing for the world during that time. So he played around with these frogs and their legs after they had been dissected, and he would kind of connect them and see what happened when he passed a current running through them, and he would notice that the legs would move and they would twitch. And this was novel information. We, as people, had never known what had done this before. It was kind of even a faux pas to dissect anything, humans, let alone animals, except for food, of course. So this was new, especially with this type of electricity running through it. So he finally created this one experiment. There was a storm going on, so he had a lightning rod and he attached that down to his frog legs to see what would happen, to make sure this was something that happened not just in his lab but in general in nature as well, to see what the underlying cause of us as life is. So when that storm came, it passed, and sure enough, a lightning bolt hit the rod and it made the legs move, and then this kind of changed everything. From this moment forward, it kind of became known that there was some type of electricity that is flowing through us, where this was, no one had thought of this before, maybe, but there's no idea to really know. Now, at that time, they're arguing, if it's the same as normal electricity, or do animals have a specific life spirit. I guess philosophically we can still have that argument, but they had found out that the electricity is the same running through us and running through circuits. And once this became, he wrote a paper, it became published, it was very well known amongst the intellectuals and also the social elites. This got to the point where actually people later on, a few years later, would start to have like cocktail parties where the main event was electrocuting these frog legs and watching them jump after they had been dead, because this was such a novel idea. Some people were definitely grossed out. Could you imagine that? But I mean, this was such a novel idea, and it got to the point where people kept pushing that forward and forward and forward. His nephew, like a decade or so later, because these kind of parties or even like little festivals became a big hit, his nephew took it to even the highest level, to where they would kill convicted murderers like nothing. And so he was like, let me see if I can reanimate this person back to life. And so after they had, done what they did to murderers during that time, he got the body and would try to electrocute it to bring it back to life. And obviously that this person didn't come back to life. However, definitely some of the muscles of this person twitched after he had already been hanged, which kind of led to many questions. People were thinking like, okay, is it possible to bring my loved ones back to life? I mean, wouldn't you want to do that, during the 1800s? We obviously know that that's not possible now, and not through what they were doing at least. But it did spark those kind of questions and fear in people. And that is, of course, where the main story, Frankenstein, came from Shelley. And she was a bright person, and she was young. I think she was like 18 when she wrote that. Just a brilliant person, bringing these ideas that were common during that time and just letting it be known to all of us. Now for us, we can look back and be like, oh, it's just kind of a silly story with certain themes about, I don't know, maybe the ethical standards of science, or maybe being careful with how we play with things that we have little information of. But also during that time, it was kind of a real fear that we could, do that, and there could be people like that were reanimated, which is kind of crazy. Who knows, maybe in the future we can think of other situations like that. But I think it's pretty cool. And actually, if you've ever heard of the term galvanize, that's kind of where it comes from. Exactly from that, to be, I guess, excited about something. So that's where that comes from. So there's my little history lesson mixed with science and a little bit of English class, I suppose. Take the other stuff that I'm not good at with a grain of salt, but I just think it's pretty interesting. Hopefully you enjoyed this. Now on to the actual problems. Let's move on to the actual problem. Let's start off with what we know and what we're trying to figure out. So we know roughly the charge. We know what the charge is, however, it's not in our favorite units. So we have 1,000 sodium ions. And then, of course, we have 6.5 microseconds. What are we trying to figure out, though? We're trying to figure out our current. What is that? So write down what you know, what you're trying to figure out, of course, with all problems, especially physics ones. Let's find what connects these things together. Remember, current is equal to the charge over our time. However, these are not the units that we really like, not for these kinds of problems. It's like saying you're using feet instead of meters for a physics problem. Can you use feet? Yes, you can. However, we prefer meters, of course. So sodium ions, are they a charge? Yes, they are, but we prefer coulombs. So let's remember how much a charge, one positive charge or negative charge, is related to a coulomb. So you remember that one electron is 1.6 times 10 to the negative 19 coulombs. The positive charge is the same, except it's positive. In these instances, we just use the absolute value. So 1 sodium ion equals 1.6 times 10 to the negative 19 coulombs. So this is our ratio, our comparison, to get this in coulombs. So to find our answer, we just have to plug everything in and then use dimensional analysis to figure everything out. So we will write 1,000 sodium ions over 6.5 microseconds. Now let's use a little conversion. Here, let's get rid of the charge first. I want to get rid of this, so I'm going to put this down here. So I know that one sodium ion is this value, so 1.6 times 10 to the negative 19. Please be careful when you put this in your calculator. Make sure you use the correct parentheses. And then, so that's gone, boom, boom. Let me write that out. We also want to get rid of time. I definitely want 1 second down here. I want seconds down here, and I want to get rid of the microseconds. You could just do it down here if you really want. Just turn this into 10 to the negative 6. However, up here, I know how many microseconds are in 1 second. Well, 10 to the 6. So 10 to the negative 6 down here, or 10 to the 6 up here, they are equivalent. It's the same. So then you can cancel these out. Goodbye, goodbye. Now, when you plug this in and you do it correctly, if you round to the 10th place, this should be 2.4 times 10 to the negative 11 amps. Perfect. On to the next tricky problem. Okay. Let's write down what we have and what we're trying to figure out. So right here, we're trying to find electrons per minute. Electrons per minute. Now we haven't done this before exactly, but let's think of what that entails. Electrons per, so some type of charge per some type of time. Does that remind you of anything? Yes, that reminds you of current. It is some type of charge over some type of time. So that is exactly what we're trying to figure out, except we're trying to do it in electrons per minute instead of seconds. Usually we use coulombs over seconds, which gives us amps, but now we're trying to convert amps into electrons per minute, which is a little different. Let's write down what we have. We have a 9-volt battery, so V equals 9 volts. And then we have a 1.6 ohm resistor, so R equals this. So to try to figure out the current, of course, this is the equation we use to get this type of current. However, using the material we have, we need to remember that V equals IR. And if we manipulate that, we should get the equation I equals V over R. Plugging that in, of course, we get 9 volts divided by 1.6 R. If you do that, you should get 5.625 amps. Good, if I was trying to find amps, that would just be it. However, I don't want amps. I don't want coulombs over seconds. I want electrons per minute. Now, is that oddly specific? Yeah, it is, but I'm a teacher and I can do what I want. Also, I think it's cool because it lets you understand like the actual number of electrons that are moving, which is a mind-numbing number. I mean, you'll be able to calculate it and you'll just be like, oh yeah, that's a big number. But it's just like, can you think of such a number? Let us convert. So this is going to be 5.625 coulombs per second. I need to convert this to electrons and this to minutes. So let's do minutes first. I want 1 minute down here, 60 seconds, bye-bye. And I need electrons on top. So 1 electron is going to equal 1.6 times 10 to the negative 19 coulombs. Again, we use the absolute value when we do something like this. For a positive ion, this would be positive. For a negative one, this would be negative, but let's just use the absolute value. if you do this math correctly, you should come out with a number. I would equal, and round to the nearest hundredth, 2.11 times 10 to the 21 electrons per minute. Oh no, that looks like a plus sign. Minus sign. Real big minus sign. Hopefully that helps you out. Compare that to a mole. It is a very small fraction of a mole of electrons. However, 10 to the 21, remember, 10 to the 6 is 1 million. That's insane. That's that's a lot of electrons. So that's what we're doing every time we plug something in. That's how many electrons are moving per minute. Hopefully you can visualize that. I know I struggle, but let's hope it helps. Okay, let me try to help you out with the conceptual problems. Here, let me show you this one right here. So moving an electron, what will happen to it? So let's just say I have some positive charge. It doesn't matter what the electric field is, but of course, starting positive, it moves out. Everything moves away. Something like that. If I had an electron just floating around, if I move it in either direction, what is going to change? The mass, the charge, or the potential energy? So if I move the electron from one direction to another, it's going to stay an electron. It's not going to change its mass or its charge. Even if it moves closer, it's not going to change its charge. An electron will be an electron. So the only thing that will change is the potential energy, either going towards here or away from here. I mean, whichever direction, you just know that there will be a change. Similar to how if you had some kind of stone, and you did work, okay, and the gravitational field here, imagine this is a cliff, the gravitational field here is going down. If you move that stone in either direction, either up or down, you will change the potential energy. You're not going to change the mass of it or anything else. Just depending on how much work you do, you're going to change the potential energy. So hopefully that is clear to you. Something else that might be helpful now, oh, you're gonna see my artwork. Let me see if I can do this correctly. Let's just say I had some ladder. Oh boy. Oh boy. And then I had some slide right here that came down with some pillars. Into some basin filled with a bunch of water. Some pool. And then we have some water. And then beneath we had some little pipe. That fed the water up top, so that when you go down, you can actually fall down instead of scraping your skin against the water slide. So if I had some pump, you have fun at a water park. This is Arizona after all. You go down, woo, have fun, and then some of the water gets pumped back up, and this is the slide that keeps forming. So let's imagine this is similar to a circuit, which it is analogous. Let's try to find out what the battery would be and what the voltage is. So if I had some pump right here, let's just, I don't know, create a fan, like a 4-leaf clover, I guess. Some fan right here that pushes the water from here all the way up. That would be the battery, okay? Because if this was not here at all, okay, the water would just start up here, fall down, and then it would want to chill down there. Similar like a rock. If you dropped a rock, it's going to want to stay down there unless you have something that brings it back up. Here we have a pump to bring the water back up, so that is like our battery. Brings the water back up. It creates this, it's this energy source that does this. Now, when we think of voltage, let us think of the difference in potential from here and here. Of course, if I put some bit of water, some droplets down here, they're going to want to fall. Similar as if I grabbed some rock and placed it at the top of the cliff, it's going to want to fall. And when you let it go, it will fall, and when you leave some water up here, it will fall. If you place some water right here in the pool already, it's not going to really want to move in the vertical direction. It's going to want to stay. Same thing with this rock. Rocks on the ground want to stay on the ground. They only move unless you have some energy source that changes that potential. So the water will want to remain down here in the low potential unless you have something that forces it to come to this high potential, and then it will want to go down. Similar to you having some sort of circuit. Remember, this is plus, this is negative. This is a very simple circuit without even a resistor. So if I had something right here, imagine this at the top, the charge is going to want to go in this direction. It's going to want to flow in this direction until you reach right here. Now, if there was no battery there, it would stay just like at the bottom of this pool. But because we have some battery, it will allow the charge that's ended here to continue on that cycle, similar to this. Of course, this is simple. Think of like if I had something to obstruct it, like some bumps or some turns, think of that as a resistor. And the reason why we draw it like this is because this adds resistance. If there was no resistor there, it would be a straight line, but because it's jagged, that makes it harder for the current to flow, which could be very useful. Hopefully this helps. I will go over a few problems later. I hope this helps. I hope everyone has a great day. Good luck.